Hello interwebs, welcome to Let's Fix Computers. I've got a HP 14s-dq laptop here that does not power on. So I believe we've got just no power at all. This is a bit beaten up, this. You can see that this corner's taken a knock at some point in its lifetime. According to the customer, this does not coincide with the damage, or rather the problem. It's been like that for a while, so... But that doesn't mean that that's not the cause of it. This might be something that has just been hanging on by a thread for a while and just let go. But let's plug in a charger and just see if it does anything. So we've got no light on the charger. Alright then. So let's get the covers off of this and do a visual inspection. Being a HP, we need to take off the bottom feet. This one is already missing, so we've got a screw here. Then this one, I'll just dig in under there, under one end. And when you're peeling these up, rather than doing one long peel, you want to do little peel. Otherwise, you'll stretch the rubber, and then it won't go down properly again. So we peel that back, and then I tend to just put it down again next door like that, because that keeps it in place and it keeps the glue fresh, and it means that it doesn't get dusty, it doesn't get lost, and you don't lose where it is. So let's get these screws out. Few bits of plastic because the case is a bit battered, also to be expected. Let's do some preliminary stabbing and just see if we can learn anything before we go any deeper. I'll put the multimeter into resistance mode, my black probe on a screw hole, and I'm going to check the DC input. So up in the top left corner here where the DC connector plugs into the motherboard. We've got red pins over on the right, so I'll just check one of those. Oops, I fell off. And we've got mega ohms up there, so input isn't shorted. Okay. Now I'm going to jump straight over to CPU vCore. So our CPU is here, and nearby to the CPU we've got some inductors, some MOSFETs. Inductor MOSFETs. So this guy here is probably going to be the vCore rail because there's two inductors and MOSFETs there. It's the biggest cluster of VRMs. So let's just check the input. So CPU, output from VRMs, inductors, MOSFETs, then input. So let's check up here. There's some big pads here, probably for input capacitors that are not present. Let's just have a look at those. That's reading short to ground, so basically 0 ohms. I'll check the other side, just in case I'm looking at a ground pad. And that's also dead 0. So we shouldn't have a short on both sides of this pad. So it looks like we have a short circuit in this laptop. Let's get the motherboard out, and we'll take a closer look at it. So I'll roll the intro, and we'll take this thing apart. There's our motherboard, and with the motherboard removed from the laptop, checking both sides, there's some dust here and there, but I'm not seeing any craters in it. You know, it doesn't look like anything has exploded. There's no skid marks. There rarely is, to be honest. It's always worth looking, but you'll very rarely see something visibly exploded. Not unless you're looking under a microscope. Like, if we have a look at one of these capacitors, we might find one that's visually cracked or something like that. But yeah, with the naked eye, we're kind of just doing a sanity check just to make sure nothing is blatantly wrong. And I'm not seeing anything. I'm going to take that Wi-Fi card off as well, just in case there's anything underneath it. This is a fairly compact motherboard, and there's nothing on the back. So yeah, I was about to say, they have put things under other things where they can. I wouldn't expect there to be an issue with any of those parts, but We'll clear all space just so we're seeing the full picture. There's an ancient Lewis Rossman video that I think about a lot, where he was working on an old A1278 MacBook Pro logic board, and it wouldn't, the SMC wouldn't come on, and he had gotten as far as removing the SMC from the board, which is a fairly major operation because now he's got to reball and reattach the same SMC or another one. And it was at that point where, on closer inspection, he still had the heat pipe on the board, and he realized there was corrosion underneath the heat pipe, which is a 2-minute fix with a toothbrush. But he just hadn't checked, and that's the thing, is just, you know, if your vision of the board isn't obstructed, then sure, fine, leave stuff on. But if there's anything that might be obstructing your view, take it off the board, because it might be hiding something that you haven't spotted. So I'm going to bring this under the microscope and show you those measurements that I took earlier on in the video, and let's see if we can spot anything else. Here's the area that I was measuring. If we look a little bit over here, you can see our CPU, and this is CPU vCore. So what we have here, working from the input to the output, we've got the main power rail coming in here to these two MOSFETs. Then these two MOSFETs are stepping the power from 19.5 volts ish down to, like, you know, 1 volt, say. The power then goes through these inductors that smooth out the stepped voltage from these guys, and the outputs are tied together into this output plane here. There's also some big capacitors here, or just a big capacitor, and then that power plane goes through all of these vias. You can see massive via stitching because this is low voltage, high current, so you need lots of connectivity. That goes down into the inner layers of the board and into the CPU. So this is how we figure out where vCore is. We start from the CPU and we work backwards through the VRMs to where power is going into the MOSFETs. Something that we do need to watch out for is the case where you have high side and low side, but that's getting pretty rare these days. These are DR MOSFETs. So these MOSFETs have a high side MOSFET and a low side MOSFET in a single chip. So there is a MOSFET here switching the high voltage into the VRM, and then there is also a low side also in this chip that switches the ground onto the VRM. Now, if you want to know a bit more about how these work, I have a video on VRMs. If you search my channel for, I'm gonna guess that it's VRM Basics, I do a very flying overview of how VRMs and how buck converters work. And if you don't understand how these work, it's worth watching that. It's not a long and complicated video, and it will give you just a basic understanding of what's going on with these things. And that's worth knowing if you're trying to follow along with these videos. So I measured this pad here and got 0, and then I measured this pad here and got 0. They can't both be ground. One of them has to be the main rail and the other has to be ground. So I would wager that this one is the main power rail because it looks like it's the main rail into these. Now it's worth noting that if I put the board at a slight angle and just refocus there, can you see how there's a bit of a tide mark on this guy? There's a bit of a tide mark there, and also just across this ITE chip you can see a tide mark. I think this laptop might have seen a drop of water at some point, but there's no corrosion, so even if there was some liquid here at some point in the laptop's lifetime, I don't think that's the cause of our problem, because once liquid goes away, on the assumption that it didn't corrode anything, the problem disappears. You can stick a laptop in a dishwasher, and if you actually just dry it properly, it'll be fine. The problem is if you apply power to it, or you don't dry it properly, because if you don't dry it properly, it will rust, and if you apply power to it while it's damp, it will corrode. So that's where liquid damage causes its problems. So even though we've got some tide marks around here, we'll be mindful of those, but I don't think that's our issue. What we have is a really nice deep short here. Let's look at that again. Yeah, there you go. Like 0.1 ohms. Yeah, it's 0. It's functionally 0. this little resistance we're seeing there is just how good a connection my probes can get to these pads. Or more appropriately, my black probe on this screw hole. Because I've got sharp probes, that one can be difficult to get onto the ground there. It's difficult to get a good connection through that tiny contact patch. So what I could do is I could put my black probe on this solder blob here for the ground point of this capacitor. And then if I measure again, we'll probably get a more reliable read. Yeah, there you go, 0.08. So that's just a little tip on just trusting what you're seeing. If you're seeing like weird results like I saw there, it's probably bad probing. And solder blobs, because they're soft, sharp probes on your multimeter can dig into the solder and get a decent connection. Also just without blunting your probes. Whereas if I just press this harder against a ground plane there, I'm just going to blunt my probes. So this is almost certainly going to be a bad capacitor somewhere. I should measure CPU V-core just in case. So let's check the output side. So once again, I'll put my black probe on ground. And if I check the output, so these guys should be acting as a barrier between the main power rail and the CPU power rail, the V-core. So if I measure the output side here, we should see a different reading. Yeah, look at that, 200 ohms. So this is great news for us, because if one of these guys has failed and dumped 19 volts into the CPU, we would expect to see a short through these VRMs. A high side short would be through one of these power stages onto this rail, and we would see the short circuit here. Now, we're getting 200 ohms there, which is quite high. Modern CPUs can be like that. You might also see low resistance, like 3 ohms, 4 ohms, 5 ohms, something like that. And that's going to almost look like a short, but 3 ohms isn't 0. That's the really important thing you've got to remember. 3 ohms is not 0. That is just the low resistance of the CPU. So if we saw 3 ohms there, that's still not the same as what we're seeing here. So we can be reasonably sure that these guys are okay. And that also means that our CPU is okay. So at this point, it seems pretty obvious that we're probably going in the direction of voltage injection to find our short. So let's go through our checklist, which I seem to change every time I make one of these videos, but whatever. So why do I believe that voltage injection is going to help us? Well, we have a short to ground, and we don't know where it is. Voltage injection is a technique used to find a short to ground by revealing the bad component. So that's why I want to use voltage injection. So is there anything else I could do instead of voltage injection? Well, we haven't really inspected the motherboard yet, so let's do a closer inspection. Let's just look around to see if we spot anything. I'll just refocus, and we're just going to stare real close at the board a sec. So here we go. I'm looking at all of these brown capacitors, looking for any of them that might be bad. And we're looking for pretty obvious stuff, because a tiny spot here, some slight discoloration, that doesn't really mean anything. That's thermal paste, where I've scrubbed my finger across the CPU. Tiny little bit of schmutz there, but that's not going to be anything. Not for a short like this. Very briefly looking at the other side of the board, but there's so little to see on the back that I'm not anticipating it. This mass of capacitors, this is all CPU V-core bypass. None of these will be it, because they're not on the shorted rail. So we did a visual inspection and we couldn't see anything. Alright, so let's move on from that. So in order to do voltage injection, we need to know where we're going to inject and why we're injecting there. So we're going to inject onto the main power rail, which we know appears here because it powers CPU V-core. Another place we could look is if we go up to the DC input jack up here. The DC input is starting up here and it's going into inner layers of the board all the way down to here, where the actual power conversion is getting done. We could sit through and figure all of this out, but we don't really need to because we already know it comes up here in order to power CPU vCore anyway. So that's where we want to inject. So we know that we can inject here because that's where our short circuit appears. We know that this should not be reading 0 ohms because this should be the main power rail. That's ground. This should be high resistance. So we've got a spot where we know our short circuit appears and we know that we are getting a reading that is incorrect. So we know why we're going to inject, where we're going to inject, and why we've selected the right place to inject. So the last thing we need to consider is, might we damage something else on the board by injecting? Something that we haven't considered already. Well, we've already checked if the CPU is shorted, and the CPU is fine. So we're not gonna inject into there, but we haven't actually checked any of the other power rails. We haven't checked if this might be a PCH issue or something like that. There's various secondary power rails on this board. We pointed out this one, CPU vCore. We've got another one here that's probably CPU related. We've got this stuff that I pointed out down here that's to do with the main power input and battery charging and stuff like that. You can see that we've got MOSFETs, an inductor, and that's going round into the battery. So this is obviously to do with the battery charger. And then we've also got, like, there's an inductor up here. There's more inductors over here. You can see we've got inductor and MOSFETs. And there's another one down here as well. So let's just quickly stab all of these other secondary rails and see if any of those are giving a weird reading that also might be our problem. So I'll just stab all of these, and realistically, we're looking for 0, basically. So there's 10K there. $700 ohms, 680 ohms, okay. Battery charger. Yep, 150,000 ohms. Cool, let's go over to the other side of the board. Five mega ohms and falling, but you know it's not going to go down to 0. And again, 700 ohms. So checking all those secondary rails, nothing popped up at 0 or like critically low. Sometimes you'll see low resistance rails at, like, say, 100 ohms or something like that. And that's low, that's not killer ohms, but again, it's not 0. If any of those are popped up at 0, then what that would indicate is a secondary rail that is shorted. And what that might show is, let's say we have a dead PCH. The PCH is getting power from, say, the 3.3 volt rail. So if we found, say, this guy here was reading 0, that could be the 3.3 volt regulator that's feeding into a dead PCH. And this is exploded and pulled the main power rail into it as well. So you get a chain of failure. And injecting on the main power rail isn't going to help us there, because we're injecting all the way upstream when our fault is all the way downstream. But we've checked all these secondary rails. We haven't seen anything else that looks wrong. So at this point, if we inject onto the main power rail, we've no reason to believe that it's going to go anywhere other than the main power rail and our potentially shorted component. So let's go ahead and inject. I've been fairly thorough about this, but the important thing is to understand that injection, it is... I always say, oh, it's not a magic bullet. It kind of is, really. It's a very, very useful technique, which is why you see it so often in these kinds of videos. But it's also really not uncommon to see tech support threads where someone has just like, oh, I injected onto the back of the CPU. And you go, why? And they go, to find the short. It's like, well, why would you inject onto the back of the CPU? Why is that going to go into the shorted rail? That's not shorted. And that's the problem. This is why we have to be so thorough, is because a lot of people aren't quite understanding the problem. You have to actually understand the layout and realize what's going on there. That's the key. So I've got the crocodile clips from my power supply here. I'm going to stick my black probe on a ground screw. I've set my power supply to 1 volt and 2 amps, and I'm going to be using my in for a P2 Pro thermal camera to spot this short circuit, and 2 amps should be enough for that. We can turn it up if we need to. So let's switch on the power supply. And when I touch the red probe onto that shorted pad, we're going to see the voltage drop. Well, we should see the voltage drop. Theoretically, it would go down to 0 because we're in a dead short. The potential difference between positive and negative becomes nothing, so the voltage is 0. And then the amperage will go up as high as we have allowed it to, which is 2 amps. But in reality, when I stab this crocodile clip, we're not going to get a great connection. So it won't go down to absolute 0, but it's going to go as low as it can given the connection it has. So let's do a stab now, and you'll see that happen. There we go. So we dropped to 0.3 volts, and we went up to 2 amps. So let's point the camera now and see if anything is getting hot. My hand is there. Is that something in the lower right there, just below my hand? Might be a reflection. If I release, it goes away. So yes, there was a heat signature around there. Let's look closer. So someone down here went hot. Let's go again. There we go. That's 2 guys there that got hot. Let's come under the microscope and see what this actually is. So what we saw was this guy and this guy heat up. Now, this is a current sense resistor. It's a 0.1 ohm resistor. And those 2 vias there and there, those are sense wires that are coming off of each side of this, and a power management chip somewhere, possibly this guy here, maybe, is reading a tiny voltage drop across that to measure the amount of power going through this resistor. This doesn't have a path to ground, so it cannot be the fault. However, it is a major bridge through the system. So this was probably warming up slightly because power is flowing through it to get to the short circuit. Now, the other guy that was warming up was this guy here. That's a capacitor. That does have a path to ground. So it's almost certainly the culprit. So let's see if we can get a really good close-up view of that. There we go. So you can see that that resistor is heating up because the power is finding a way through it. And then that one capacitor is getting warm. Only a little bit warm, but I can make that go nuclear. If I step the power supply up, let's take that up to 3 amps. Now we'll be allowing more current to flow through it, so it gets hotter. There you go, nice big flare there now. Alright, so we found our problem. I'm going to clear up the injection stuff, and we're going to take that capacitor off the board. I'll come in with the hot air now. I'm at 400 degrees maximum airflow, and I'm going to be blowing roughly away from this plastic connector in the lower left. And we're just going to take off that capacitor, and I'm going to take off the one next to it so I can measure the value, because these 4 capacitors are almost certainly identical. And I'm guessing 10 microfarads. Because it's always 10 microfarads. There's one. And there's 2. So let's measure our faulty boy and confirm that he is shorted. Which it is. And this one presumably is not shorted because it was not glowing. Yeah, that one's showing high resistance. Cool. So now I'll go up to capacity. And this one we won't get a read on because it's shorted. But if I measure this, we should find out what the value on it is. So let's just get that comfortable. There's lots of tricks to stopping these from jumping about. I can't be bothered to do any of them. And it's 10 microfarads. Cool. So they're 10 microfarad capacitors. The voltage rating on them is probably going to be like 25 volts or something like that. They're sitting on a 19.5 volt power rail, so really we want a rating of 25 volts or higher. Typical values are like 25, 30, 50, that kind of thing for ceramic capacitors like this. So you don't need to worry about the exact voltage. It's just got to be equal to or greater than the rail that it's sitting on, preferably higher, just so it's got a little bit more endurance on it. If you put on a capacitor that is 20 volts on a 20 volt rail, it'll be okay, but it's going to get hammered. Whereas if you put in a higher rated capacitor, like say a 50 volt capacitor on a 20 volt rail, it's going to have a very easy time. Let's clean up these pads now. As to why it failed, well, these are ceramic capacitors, and they can fracture because they're ceramic. And laptops get a lot of bumping and jostling, and they get flexed, and this laptop had been dropped at some point in its lifetime, and so on and so forth. So it's easy to see that a little bit of shock would just put a hairline fracture into a ceramic capacitor, and that's just got to bend into the wrong angle. And as soon as it bends to slightly the wrong angle, it shorts out and then fuses itself together. I'm not going to bother wicking those down, actually. I'm just going to hot air the new capacitors on. So now I'll come in with the hot air again. This time I'm turning my airflow down to, about a third or so, just so I don't blow these capacitors away. I'm being a bit leery by trying to put them both on at the same time. This one's trying to get away. And we'll just gently heat. There we go. And once the solder melts, as you can see, it kind of just magnets into place. The surface tension just pulls everything into alignment. Nice. I'll just touch the ends of those with the soldering iron again, just to tidy up the end caps. There we go. And now some alcohol just to clean up. I'm just going to toothbrush all of this out. You'll never get a cotton swab into there. Let's do one last test just to make sure that we're not somehow still shorted to ground. We should make sure we've actually solved the problem here. So I'll stab ground and that same pad again. And now we're seeing high resistance here. Looking like about 100,000 ohms, 100 kilo ohms. Perfect. Cool. I'm going to clean up the thermal paste on this and get it all reassembled into the chassis again, and then we can test it. Alright, let's check for charge. Boop. There we go. Oh, it came on and went off. I'm just going to replug the charger because I haven't replugged it since I plugged it in at the start. So the charger might have just cut out. Okay. No charge light. Does it do anything now, though? No. Did something else go? Did something else just let go? That's extremely dismaying. That's what I get for putting the screws in. Or at least the screws that would go back in. These front ones are all knackered. Right, sanity check. Did we just explode another capacitor? Power is unplugged. Ground. Main power rail. I don't believe it. Another capacitor has gone bang. We checked it. We checked our work. Just another one just instantly went pop. Pain. Let's pull it out again. Oh, God. No, actually, no. I'm going on lunch. I'm going on lunch. See you after the cut. Ugh. Delicious. So I'm just going to immediately stab it again with 3 amps and we'll see what happens. My money's on the other capacitor that I removed in order to measure it. Maybe just some extra heat stress on that upset it. Okay, so it is in the bottom right again. It's not the one I thought it was. It's in that cluster though. Okay, there it is. So it's the first capacitor nearest the battery charger inductor. Let's take a look under the microscope at that guy. So it's that one there. I'll just change it out. I've not had a cascade like this before, where you fix one and then another fails. It wasn't shorted initially. Like, this isn't a double failure. This is a subsequent failure. Because remember, after I replaced the capacitor over on the left here, that lighter coloured one, after I replaced that, we checked for shorts again. We checked our work, and the short was gone. And when I plugged the laptop in, the light came on for a moment and then went out. So maybe this one just wasn't far behind. In any case, let's just zap it with the hot air. Alright, and once again, we're not shorted. We've got high resistance on the main power rail, 22 kilo ohms, and that's just jumped up to 100 kilo ohms. Okay. If I plug this in and another capacitor goes pop, I'm going to throw this across the room. Right, do any other capacitors want to explode? Let's find out. Ah! Okay, we have a charge light. It's kind of dim on the camera under the lighting, but it's there and it's staying on. Cool. Alright. Okay, HP. Live. Live once more. It's taken its time to post, but it's probably got a RAM train and stuff like that, so let it cook. Oh no, we've got an error code. The caps lock LED is flashing. 1, 2, 3. 1, 2. That's 3 long flashes and 2 short flashes. This was almost perfect textbook, this laptop. I was recording it expecting it to be textbook, which is why I was going through all the motions of talking about injection and stuff like that. I was like, oh, y'all have seen me do this before, so let's actually like explain it all properly. Let's make a lesson out of this because it's an easy one. There we go. It was just a memory module that wasn't seated properly, so that is now booted up. Clock needs to be set. However, the laptop now works. So thank you everyone for tuning in. That one was a pain in the backside. However, it does now work. I warranty my work because obviously after looking at this, the obvious question is, well, is it going to blow up another capacitor now? Or was that it? I've not seen a cascade like that before. But again, this is why I warranty my work. I will say to the customer, you know, hey, by the way, I had to sort of fix this twice over. If it dies, come and talk to me and we'll look at it again free of charge. So take it away, see how you get on with it. I very rarely get callbacks on these kinds of jobs, but this might be the one that comes back in, but we'll see. So in any case, thanks for tuning in, everyone, and I'll see you next time. Bye.